Okay, now we're moving on to chapter 27. Chapter 26 was mainly about current and voltage and resistance. Here for chapter 27, now we're getting into circuits. First packet is going to be about resistor circuits and multiple batteries and stuff like that. We're assuming that simple resistor circuits you already know. So if you need to review that, you should do that. Resistor is the load, right? It's another word for that. Capacitors, we've studied. Battery, again, this is just review. Some of the different symbols that we use for resistors and batteries and that sort of thing. Okay, just checking that the microphone is working appropriately. Okay, and so again, resistors in series, the equivalent resistance, you add them up. Resistors in parallel, equivalent resistance you get by doing the flip, add, and then flip. And so there's a summary of capacitors and resistors in series, in parallel, you know, the current, the charge, all that stuff. Okay, ideal EMF. An EMF, an ideal battery, has zero internal resistance. Most batteries do have internal resistance though, and so what you'll sometimes see is that next to the battery in the circuit there's a little R right next to the battery, and sometimes there's even a box around both of them together. They're telling you that's the internal resistance of the battery. And so that's really what you need to know there. Okay, EMF devices. EMF devices, like batteries, they do work on charge carriers. They do work on electrons, because electrons are the things that are going to be moving. They push them through a circuit, right? Or they push them to a certain point, like in a capacitor circuit. They push them until they're collected on the capacitor plates, something like that. And so, how do we analyze a circuit? All these things. Kirchoff's laws. One, the loop rule. That is, when you go through any loop, all the voltage should add up to 0. And then the junction rule. Going into and out of any junction, the current has to be the same. And we're going to be really putting that to the test here with these problems that you're going to see. Okay, so there's a summary here of how to use Kirchoff's laws. And so when you have multiple batteries, you sort of pick what you think the current is, and then you write equations for each of the loops, and you write equations for the junctions, right? If there are only 2 loops, there's only one real junction that you can use. If you write the equation for the other junction, it turns out to be the same equation. And so there's a little bit of an example here, and it says write the loop rule equation for this circuit, right? So it's just a real simple circuit. Let's take a look. Okay, so when I'm doing this loop, I'm going to go around in the same direction as the current. That was a messy resistor. But if I go around this way, right, going through the battery this way, I'm adding up that EMF, right? So it's plus that EMF, and then now, since I'm going in the direction here, right, so this is plus, minus, I'm losing potential. This is plus, this is minus side, so I'm losing potential here, so I'm going to lose this I. Right, I can be lowercase or capital. Usually lowercase is a changing current, but we can do it either way. Times little r, and then here going from plus to minus, I'm losing potential again, so minus, same current though, times big R, and that's it. So then to find the current, this all equals 0. To find the current, then I solve for I. So I is going to end up being EMF over little r plus big R. Okay, and I plug in my numbers. This ends up being 10 and 4, so it's 2.5 amps. Right, can you guys see that? Yeah. Right, and then now for this one, this is where things start getting a little bit tricky. In example 2, because now we have 2 batteries. So how does this work? This graph. So, the graph is, so this is 2.1 volts, and this is 4.4 volts. We can get that from the graph. That's the potential drop from one to the other. Let's just say for a minute that you didn't know that that was the direction of the current. So you pick a direction. I mean, naturally, this is more, so you think the current's going to be going that way. But let's just say counterclockwise is our direction for the current. Okay? And then we fill in, this one's 4 ohms. This one is 1 ohm. This one here, R1, is 1.5 ohms. All right, 1.5. Okay, so if I'm going around this way, here's how this works. If I think the current's going this way, let me start here at A. If I go backwards across a battery, that's actually a minus. I'm subtracting the voltage from that battery. And then as I'm going across here, since I think that's the direction, now I'm going to also be subtracting 1.5 times I, right? That's the voltage being used up by that. Here, the voltage being used up by this is 4I, and then the voltage being used up by this one is 1I. And now I'm going the correct way across the battery, right? Negative to positive, up. I'm adding potential going this way. So plus 2.1 equals 0. Okay, and now all I have to do is solve for I. And so this ends up looking like negative 2.3 volts plus I times 6.5, or negative, what does this end up being? Negative 6.5. And then when I solve this for I, this ends up being 2.3, or positive 2.3, right, because you add it over negative 6.5. And we end up with this negative 0.35 amps. What does the negative mean? The negative means we picked the wrong direction for the current. But this is the magnitude of the current. So that means that the current here is really this 0.35. Next is example 3. And in example 3, this is like the capacitor monster maze problem that we had, except this time it's the resistance monster maze. And so we've got all the batteries are 4 volts, all the resistors are 4 ohms, and so you're just looking, can you find a path that goes through one battery and one resistor, or you know, 2 batteries, or only batteries and 1 resistor, and it turns out that that you can, right? And hold it up, it looks like this. That's the path that you have to take, and you'll see that you are only going through batteries, and then through that 1 resistor. And you pick the direction for the current you think it's going. And so you're adding and subtracting all the batteries, whether you're going negative to positive or positive to negative, through that battery. And all those voltages plus 4I equals 0. And then you can solve it, and you get that. Right? Okay, so here's where things get interesting, because now we've got 2 batteries and we've got 2 loops, or 2 circuits, actually 3 loops, right? 1, 2, and 3. And so what we're going to have to do now, so how many currents do we have? We've got 1 current in this wire, so we'll call this I1. We'll call this I2, and we'll call this I3. I'm going to assume that the current is going this way because this voltage is more than this voltage, so I'm doing something like this. And so as a result here, I1 is equal to I2 plus I3. Right. But I'm going to rewrite this as negative I1 plus I2 plus I3 equals 0. All right. And what I'm trying to do is I'm going to write 3 equations where I have I's here, and then over here on this side, something else. So now let's take a look at the junction, or the loop rule, and let me take, let's see, this loop here is going to be one to use. So starting from here, I got 12 volts, and I'm subtracting, I'm going this way across this resistor, and so minus, right, this is plus minus, it's a potential drop, so minus 5 times I1, okay, and then this way, so this is 10 times I3 equals 0. Now again, I'm going to rewrite this with coefficients of the i's. So This will be 5I1 plus 0I2 plus 10I3 equals 12. And I can make it all positive because this comes over here and is negative, so I make the whole thing positive. That's my next equation. Okay, now I'm going to write an equation for going all the way around this thing. So starting here again, I've got 12 volts minus 5I1 minus 5I2 minus 8 volts, because I'm going this way, right, on the wrong side, so this is plus minus. This is a potential drop going from positive to negative, and so equals 0. So I subtract that 8. This 12 and 8 is negative 4, so I bring that over to that side. So I've got 5I1 plus 5I2 plus 0I3 equals 4. Okay, and so now I've got 3 equations and 3 unknowns. And there are multiple ways of solving this. You could do substitution, or subbing things in different places, and that takes a little while. Or you can do a matrix, and that's what I'm going to show you now, just the process. And for your information, on the next page, after example 7, there are instructions there for how to do a matrix in your TI calculator. But let me write it out this way. And what I'm doing is I'm just writing these coefficients. So this is like -1, 1, 1, 0. Let me put this one here. So this is 5504. And this one is 5, 0, 10, 12. And in case you forgot how this works, the idea is I am multiplying this by something so that when I add it here, I can eliminate. And so I just want to end up with a diagonal here, right? So I want to eliminate this 5. And these two are the same, so I could do this in one fell swoop, right? So this is, I'll make this -5, 5, 5, and then 5 times 0 is just 0, right? So then over here, my next, I can leave the top. And then adding this, -5 and 5 is 0, 5 and 5 is 10, 5 and 0 is 0, or sorry, 5, of course. And then that's still 4. Adding -5 and 5 is 0. 5 and 0 is 5. 5 and 10 is 15. And then that's 12. Good. So now I've got zeros here. Now I want to get a 0 here. So I'm going to divide by 10. And I'm going to subtract. Okay, so I've got -1. And then this is -1, so that's 0. This is -1/2, plus that makes it +1/2. And this is -0.4, so this becomes -0.4 here. This remains the same. This is +10. 0, 5, 15, and 12. So I want to go this way now. So I'm going to take this and divide by 2 and multiply by -1. So this and that, so the top is still the same. And then this is still 0, 10, 5, and 4. So now this plus this is -5. So this is 0. This is -2.5, so this becomes 12.5. And this is -2 plus that, so that's 10. What I'm going to do here is I'm just going to replace this, make this 25 and 20, and then I'm like, hey, that, I can just replace this with 5 and 4. Right. Okay, so now I want to get rid of this and these things. So if I just multiply this by -1 and then add that, then these go away. And so my new matrix is this. This is 10, 0, 0. This is interesting. And then 0, 0, 5, 4. Again, now I can multiply this by -1/10. So -/10, -/10. I add these. This goes away, so I'm left with -1, 0, 0, and -0.8. 0, 10, 0, 0, and 0, 0, 5, and 4. Okay, and now let's take a look at what this means. This means negative I1 equals negative 0.8. So I1 then is 0.8 amps. What's that? This equation is saying that 10 times I2 equals 0. Okay, so that means that I2 has got to be 0 amps. This equation, that's the coefficient of I3, so 5I3 equals equals 4, jumping ahead of myself here, 4. So that means I3 is equal to 0.8. Okay, and if we look at our circuit, that makes sense. It works with the junction rule. Okay, and so I mean, this was a lot of math, a lot of just matrix solving. The physics is really in setting up the equations in the beginning. Okay, and so here now we've got this current. I'm going to assume there's current going this way, actually, because this is. Actually, I'm going to assume current's going this way. So I'm going to call this I3, and I think there's current going this way, so I'm going to call this I1. And this one here I had made I2. Okay, and so looking at this junction, I1 is equal to I2 plus I3. All right, 2 and 3 are coming in here, and then I1's going out that way. So I've got negative I1 plus I2 plus I3 equals 0. Okay, and then I'm going to take a loop. Let's see, I can go around this loop here. All right, and so what I've got here is plus 6 plus 8 minus 12, right? Because I'm going this way, that way, and then backwards across the 12. So plus 6 plus 8 minus 12 gives me a 4 volt potential difference, ultimately, and then minus 5I2 equals 0. And so this is 0I1 minus 5I2. We'll make this plus. Plus 0I3 equals negative 4. All right, so here's my next equation. And I've got a nice little loop right here, so I'm going to do this. This is 8 volts equals, or minus, let me just write minus 10I3 equals 0. And so this is 0I1 plus 0I2, say plus 10I3 equals 8. 3 equations, 3 unknowns, and there are other equations you could set up. I mean, this one's got to be the same, but you could even take like this loop if you went around this way. Just be careful if you're going across the in the opposite direction of the current, then you've got to actually add, because what we're saying here is this is plus minus. Going from the negative to the positive side of a resistor, the potential difference, you've got to add that. All right, and I mean, if you want to see the matrix, I can show you later, or how to solve it that way, but solve it one way or another, and the answer you should get is that I1 is 0.8 amps, I2 is 0.4 amps, and then I3 is 1.2 amps. Okay. There's another question here. It's what's the potential difference between points A and points B? Well, this one is actually easy. Just from here to here, it's a difference of 14 volts, right? So delta V from A to B is potential difference of 14 volts. All right, so again, we've got this set up. I called this I1. I predicted I3 was going this way, because this is like, 12 and 8 here. I figured that would probably overpower that one. But this one would overpower this one, so I think this current is going to go this way. So I called this I2. Right? And again, there are different equations you can set up. The junction rule equation is going to, again, be like I1 plus I2, sorry, I1 equals I2 plus I3. Let's take this loop, this big outside loop, and take a look at how that would work. If I start here, I'm adding 12 volts right away, so 12 volts, and then I'm subtracting 10 I1, and then I'm still in the direction of the current here, so this is minus 10 I3, minus 6 volts, minus 10 I3 again, and this way, and then I'm going this way, 10 minus 10 I1, all of that equals 0. All right, so part of what we're going to do here is look at simplifying this whole thing. You know, so you got to simplify and combine like terms, and I think what you end up with here then is negative 20 I1 minus 20 I2. This would be plus 0 I3, of course, equals 6. All right, 12 and 6 negative. So let's make it all positive, because you could subtract the 6 over there, and so that's your next equation. And let's write an equation for this, actually. Let's go this way so you can see how this works. So I'm going backwards across this resistor so you can see that. So let me start here. So right away, this is minus 10 I3 minus 6 volts minus 10 I3. That's going this way. And then plus 8 volts. And now, since I'm predicting the current, if the current's going this way, then this is the plus and that's the minus side of this resistor. But now I'm going from negative to positive side of the resistor. So this will be plus 5 I2 equals 0. All right, so the total voltage here is 2. All right, so 2 volts minus 20 I3 plus 5 I2 is 0. Okay, so this is going to be 0 I1 plus 5 I2 minus 20 I3 equals negative 2 volts, and that's your next equation. But again, you could do an equation for this one as well, but I wanted to show you this, what it's like going backwards through a resistor if you're going the opposite direction of the current. One way or another, when you get to the end here, I1, and this one gets pretty messy if you're trying to do this by hand, I1 turns out to be 31 over 60. I2 turns out to be 1/3. And I3 turns out to be 11 over 60. Right? And so these are the answers to this problem. And then from that, you can find the potential difference between here and here. It's going to be 8 volts plus 1/3 of 5. All right, so I guess 8.6 volts, something like that. All right, we'll try this one more time. The first time I did this, I hadn't plugged in the microphone, so the sound was not working, and then I just did this whole explanation again without turning on the camera. It looks like it's on now. Let's try this again. So here's number 7, and this should look familiar. We did this with the capacitors, but now the adding should be a little bit more natural, right? These two in series, that's 2 ohms, but then the 2 in parallel with the 2 is 1, but then now the 1 in series with the 1 gives me 2 ohms, etc. And we're just adding up, so it's like 2, 1, 2, 1, 2, 1, all the way until we get to this point. The entire equivalent resistance is 2 ohms. Okay, so I is V over R, so 6.4 divided by 2 gives me 3.2 amps. That's how much current is going through this resistor. And now the current splits. It splits, and it's even on both of these, right? We could say, okay, it's 3.2 amps going through this whole thing, and so we could figure out what the potential difference is across this whole thing, right? And then divide by 2, or divide by the current here, the resistance here and there, and so you get 1.6. Really just gets cut in half, and then so it's 1.6, and then it gets cut in half again and again and again and again, so that the current keeps getting cut in half all the way down until it's 0.1 ohms or 0.1 amps in these last 3 resistors. Okay, and I think that's it for number 7. The next page, the next slide is instructions for finding or solving matrices using your calculator. And 27.8 is the problem with using meters. Anytime we use a meter, we are doing something to the circuit, and anytime we change the circuit, or anytime we add something to the circuit, we're changing it. So how do we reduce that as much as possible, the change, and yet still get an accurate reading? When we're measuring potential with a voltmeter or a multimeter, which does everything, the multimeter or the voltmeter is placed in parallel. It's placed in parallel because of Kirchoff's loop rule. And what we do is we have a very high resistance in the voltmeter so that most of the current is still going through the circuit. Okay, but current has to be measured in series. You have to break the circuit and put the meter into the circuit. But you still want most of the current going through the way it was before. And you want the meter to act as much like a wire as possible, so very low resistance. And then an ohm meter measures resistance of an element. One way to measure resistance is using the Wheatstone bridge. It's made of 4 resistors, 1, 3, R1 and R3 are known. R2 is a potentiometer, or also known as a variable resistor. And what you do is you can change the resistance on it using a dial or something like that. And that can be used to measure Rx, because you change the dial, you change the resistance on one until you get a 0 reading on the voltmeter. And then you can use this formula, right? R1 times Rx is R2 times R3, kind of like the formula that we come up with before with the capacitors. Okay, and that's it for this chapter 27 packet.